Let's see what's the trend of metallic nature in a periodic table. Basically, how does the metallic nature vary as we go across a period and down a group? And if you're wondering what's metallic nature, then I hope you recall that a metal is an element that can easily give away its outermost electron. For example, sodium is a very good metal. It has one electron in its valence shell and it will participate in chemical reactions to give that away. Because by doing so, it can attain a complete octet, just like the noble gas, the nearest noble gas, neon, and therefore will become more stable. So metals like to give away their valence electrons and become more stable. So if there is an element that can easily give away its outermost electron, then it is going to be more metallic in nature. Whereas if there is another element that requires some effort to give away its outermost electron, then it's going to be less metallic in nature. So that's the trend that we are looking for. But before we begin, let's try to find out what makes it easy or hard to give away this outermost electron. Well, actually, you will recall that the electrons are held in their position because of the pulling force by the nucleus. See, nucleus has positively charged protons and they will attract the negatively charged electrons, right? Opposite charges attract each other. So because of this pulling force, the electrons are held in their position. So if this pulling force is more, then it'll be hard to give away this electron. But if this pulling force is less, then it'll be easier to give away this electron and the element will be a better metal. Well, then what does this pulling force depend on? Well, it depends on two things. First, the effective nuclear charge, and second, the distance from the nucleus. Now let's understand each of these factors in a little detail. So the first one is effective nuclear charge. This basically means effectively how many protons are pulling our electron. If the number of protons pulling is more, then the pulling force is going to be higher. If the number of protons pulling is less, then the pulling force is going to be lower. For example, if you have one magnet pulling an iron nail, the pulling force is less compared to if you had two magnets, right? What about this term effective? What does this mean? So let's understand this. Let me draw the valence electron somewhere below over here. Now imagine that this is being pulled by the protons over here. There are 11 protons in the nucleus of sodium atom. So the pulling force will be due to 11 protons. But is that it? No. See, there are some electrons in between and these electrons will be repelling our valence electron. See, these electrons are negatively charged just like our valence electrons, and like charges they repel each other. So there are 10 electrons inside, so they will be repelling our valence electrons. So our valence electron will be feeling a repulsive force by 10 electrons, okay? So it's experiencing a pull by 11 protons and a repulsion by 10 electrons. So we can say that effectively this electron is being pulled by one proton, right? Let me actually replace this. Effectively, I can say that 11 minus 10 is 1. This electron is experiencing a pull by one proton. So this becomes its effective nuclear charge, the effective nuclear charge that this electron experiences. Well, in reality, these calculations are going to be slightly complicated, which we'll be talking about in future videos. But for the sake of this video, this level of simplicity is okay. Fine. Now let's talk about the distance from the nucleus. So see, if the electron is closer to the nucleus, then the force that it will experience is going to be stronger. Whereas if this electron is farther away, okay, then the force is going to be slightly weaker. For example, if we take the analogy of magnets again, so if I take this magnet a little farther away, you can imagine that the pulling force that it will experience will suddenly reduce. So the force also depends on the distance from the magnet, right? So the pulling force that this electron experiences, it depends on how closer or how farther away from the nucleus this electron is, okay? And you know what? The distance from the nucleus is somewhat related to the number of shells, the number of shell in which the electron is. So generally speaking, in general, if this electron is in a higher shell, that means it will be farther away from the nucleus. Currently, this electron is in the third shell. If this electron were in the fifth shell, it would have been farther away from the nucleus, generally speaking. Now let's see how the metallic nature varies as we go across a period. So the two factors that decide this are 1, the effective nuclear charge, and 2, the distance from the nucleus. Now let's focus on the period number 2, the elements of period number 2. Let me bring these elements closer. Well, let's not talk about neon for now because we know that neon is a noble gas. It's not going to lose electrons. So what's the point of talking about it? Let me hide this. Okay, now first let's see how the effective nuclear charge varies as we go across this period. So first of all, let's talk about lithium. So lithium's atomic number is 3. It has got 3 protons in the nucleus and 3 electrons. If we focus on this valence electron, it is being pulled by 3 protons. But that's not it. It's being repelled by these 2 inner electrons also, like charges repel. So this electron is being pulled by 3, being repelled by 2. So technically speaking, this electron is being pulled by 1 proton effectively, right? So its effective nuclear charge, the effective nuclear charge that this electron experiences is going to be 1. Now let's talk about beryllium. So beryllium's atomic number is 4. It has 4 protons at its nucleus and 4 electrons. If we focus on this valence electron, okay, so this is being pulled by these 4 protons and it's being repelled by these 2 inner electrons. Well, this electron is in the same shell as this valence electron. So this will also provide some repulsion, but you know what? Electrons in the same shell, they provide very little repulsion. So to keep calculations simpler, I'm going to ignore this, okay? So this electron is being pulled by 4 and is being repelled by these 2. So effectively speaking, this electron is being pulled by 4 minus 2 is 2 protons. So its effective nuclear charge is going to be 2. Now let's talk about boron, the next element. Boron's atomic number is 5. It will have 5 protons and 5 electrons. Now can you pause the video and tell me what will be the effective nuclear charge experienced by this electron? Pause and try. Now if you have tried it, let's see. So see, this electron is being pulled by these 5 protons and being repelled by these 2 inner electrons. See, these 2 electrons will also be repelling, but only a little bit. They are in the same shell, right? So for simpler calculation at this level, let's ignore them. So this electron is being pulled by 5, repelled by 2. 5 minus 2, effectively we can say that it's being pulled by 3. So its effective nuclear charge is going to be 3. Now as you can see, the effective nuclear charge is increasing as we go across a period. Now that would mean that as we go across, the pull on the valence electron, that increases. This atom will have a higher pull on the valence electron than this one. Now that would mean that this atom finds it harder to lose this electron than this. Now that would mean that this atom is less metallic than this one. Okay? So as we go across a period, the effective nuclear charge, it increases. And because of this, the metallic character, this decreases. Now let's talk about the effect of distance from the nucleus. So in the video of atomic radius, we have already seen that the atomic radius reduces as we go across a period. And that's also happening because the nuclear charge is increasing, and with increasing nuclear charge, it is able to pull the shells much more closer. Okay? Now, if the distance between the nucleus and the valence electron is decreasing, then that would mean that the pull between them has increased. Now, if the pull has increased, it becomes harder and harder to give away the valence electron. That means the metallic character has reduced. So what we see is that as we go across a period, the distance between the valence electron and the nucleus is reducing, because of which the metallic character is again reducing. Okay? So because of both of these variables, the metallic character reduces. So therefore we can say conclusively that as we go across a period, the metallic character reduces. Now let's see what happens as we go down a group. So here I have elements of group number 1. Over here I haven't shown hydrogen because technically hydrogen does not belong to group number 1. And we have spoken about why in the video of modern periodic table. So go ahead and watch that first. Over here, let's first see how the distance between the nucleus and the valence electron varies as we go down a group. We'll come back to effective nuclear charge a little later. So for this, I have drawn the electronic configuration of lithium, sodium and potassium, the first 3 elements of this group. And from the video of atomic radius, you might recall that the atomic radius increases as we go down a group. Well, you can see over here, there are more shells, there are newer shells getting added between the valence electron and the nucleus. So therefore, the atomic radius, the distance between them increases. Now with this we can say that the pull or the attraction that the valence electron feels is going to reduce. We saw that with the help of magnets also. If two magnets are getting far away, then the attraction, the pull between them is reducing. So same thing will happen over here. Now that would mean that it will become very easy for potassium to give away its electron compared to sodium, compared to lithium. So that means as we go down a group, it becomes easier to give away the valence electron. That means the metallic character is increasing as we go down. So therefore, in summary, we would say that as we go down a group, the distance between the valence electron and the nucleus increases, and therefore the metallic character also increases. Now let's talk about the effective nuclear charge. So lithium has an atomic number of 3. That means it has 3 protons. So this valence electron is experiencing a pull by 3 protons, but it's also being repelled by these 2 electrons. So 3 are pulling it and 2 are repelling it. So effectively speaking, 3 minus 2, 1. This electron experiences a nuclear charge of 1. So its effective nuclear charge will be 1. Now let's talk about sodium. So sodium's atomic number is 11. That means it has 11 proton. Now this valence electron will be pulled by 11 protons, but it's also being repelled by 2 plus 8, 10 electrons. So being pulled by 11, being repelled by 10. So 11 minus 10 is 1. So effectively speaking, this electron is also being pulled by 1 proton. Its effective nuclear charge is 1. Similarly, if you look at potassium, its atomic number is 19. It has 19 protons. This valence electron will be pulled by 19, but it will be repelled by 2 plus 8, 10, plus 8, 18. Pulled by 19, repelled by 18. 19 minus 18 is 1. So effective nuclear charge for this electron is going to be 1. Now if you notice over here, the effective nuclear charge remains the same as we go down. Now this means that metallic character should not change. Well, that's not actually true. See, calculating effective nuclear charge is not that straightforward. And we will look at how to calculate effective nuclear charge in future videos. But for now, I looked upon Wikipedia. And turns out this is how the effective nuclear charge varies. It increases actually as we go down a group. Now you would say that this means that our valence electron of potassium, this will experience a higher effective nuclear charge, means a more stronger pull than the previous atom, right? Now this would mean that it will be harder to give away this electron. Therefore, potassium should be less metallic than sodium, and sodium should be less metallic than lithium, right? So basically, the effective nuclear charge is actually increasing as we go down a group. And because of this, the metallic character should reduce. Now there is a problem. Should the metallic character decrease or increase? Well, see, it turns out that the change in effective nuclear charge, this is very small as we go down. So therefore, due to it, the decrease in metallic character is small compared to the distance. The distance increases by a lot as we go down, and therefore the increase in metallic character should be more. So if you see, net as we go down a group, the metallic character will be increasing. Okay. Now let's summarize the video. In this video, we spoke about the periodic trend of metallic character. And metallic character can be measured by the ability of an element to give away its electron. Now this depends on 2 variables: the effective nuclear charge and the distance between the nucleus and the valence electron. Now as we go across a period, the effective nuclear charge increases, meaning it becomes harder to give away the valence electron. Also, the distance reduces, meaning it becomes even more hard to give away the valence electron. So as we go across a period, it becomes harder to give away the electron, meaning the metallic character reduces. Now as we go down a group, and this is where you need to be careful. As we go down, the effective nuclear charge increases, so it becomes harder to give away the electron. But the distance, this also increases, making it easier to give away the electron. So what happens? Well, it turns out the distance increases a lot, so it becomes much more easier to give away the electron. So therefore, net, as we go down, it becomes easier to give away the electron, and therefore the metallic character increases.